Greetings and welcome to the introduction to astronomy. In this lecture, we are going to talk about the beginnings of modern astronomy. Now, previously, we talked about some of the ancient astronomy, especially the astronomy of the Greeks that gave us the basis of our current astronomy. Now we will see how things changed in the Renaissance as we began to get a better physical understanding of what was happening in the solar system. So it kind of starts with this gentleman. This is Nicholas Copernicus, and he is the first modern astronomer to give us the suggestion that the Earth is a planet. So the Earth being a planet rather than the Earth being the center of the universe. So this switched us from the geocentric universe to the heliocentric universe. If you recall, Aristarchus suggested this, but it was really not considered seriously considered in early times. So what Copernicus suggested was that all planets, including Earth, orbited the sun. Now, in a way, it was a very simple model. It explained retrograde motion, which we've looked at a little bit, and we'll look at a little bit more coming up, in a much simpler way. It did not need those complex epicycles to be able to do it. However, he was not able to completely eliminate epicycles, because while he put the Earth at the center, he did still rely on circular orbits. So let's look at his model here. And what he gave us was, here is the sun at the center, and then Mercury, Venus, Earth and Moon, Mars, Jupiter, Saturn, and then the great sphere of stars out around the end there. So the sun was at the center. The Earth and planets revolve around the sun. Now, this does make a prediction. It predicts that stars will have parallax. Now, parallax is an apparent shift of one object relative to another. This is something the Greeks knew about and is likely one of the reasons why they discounted the heliocentric model. We'll look at parallax in just a minute in a little more detail, but this also was much simpler at explaining retrograde motion. So let's look at parallax first. How does this explain parallax? Well, first of all, what is parallax? It is the apparent motion of a nearby object relative to a more distant one. So when we look at this object here from point A, from this point A, we see it against the blue background. From point B, we see it against the red background. The amount of that shift, so the angular shift that we can measure, then gives us can be used to determine the distance. But the fact that there would be a shift is predicted by the heliocentric model. However, because of the vast distances of the stars, was not able to be detected until 1838. So long after Copernicus and all of the other astronomers that we'll be looking at, who gave us the idea of the heliocentric universe, they were still missing this key point. We had not yet been able to demonstrate through parallax that Earth was actually moving. Now, the other issue was with retrograde motion. Retrograde motion was explained by, for example, the Earth at the center here, with the sun orbiting Earth in an ordinary orbit, and that a planet would then orbit on an epicycle, and that epicycle would move, the center of the epicycle moves on the orbit. This allowed the explanation of retrograde motion, because when the planet was on the inside of the orbit, it would appear to move backwards. So this is how it is explained in the geocentric model, and the model works based on the scientific method. You can use it and make predictions as to where the planet would be. And by adjusting things like the speed of the planet in the orbit and on the epicycle and the size of the epicycle, you could then explain retrograde motion. However, it's a lot easier to explain through the heliocentric model. And here we see that here now we have the sun at the center. And we have planet Earth here going A through F, points A through F as it on its orbit. Now being a closer orbit to the sun, it moves faster. And the other planet, say Mars, moving H through N here. And if you connect, each of these are at the same time. So at point when Earth is at point A, it sees the Mars out at this point. When it's at point B, all of a sudden it's at this point. So it had been moving in a direct position. But when it gets to point C, as Earth overtakes Mars, then it appears to have moved backwards. Point D, it moved backwards even further. And by the time you get to point E, it's now turned around and started to go forward again. And then point F, it's back to its ordinary motion. So the planet is not actually starting and stopping. It's moving at a nice uniform speed in its orbit. It is just the way we are seeing it. It's just a matter of the perspective that gives us this apparent retrograde loop. So either of these explains it, but it's a simpler explanation under the heliocentric model. So was the heliocentric model, was it accepted? Certainly not immediately. It took a long time. First of all, it predicted parallax, which was undetected. There's also no sign that the Earth was moving when we go outside. It also was no more accurate than the geocentric model. Yes, it was more realistic based on what we know now. However, it was not any more accurate in terms of predicting positions. And it still required some epicycles to account for the motion because of the use of circular orbits. Because circular orbits continued to be used, that meant that you still needed epicycles to be able to account for the detailed motions. So let's continue on and look at another astronomer of this time, and that is Galileo. Galileo, sometimes considered the first scientist, and we'll come back and look at him again in the next chapter as well. And he did experiments to study the motions of objects. It gave us the idea of a concept of inertia that Isaac Newton would then incorporate into his laws. And the idea that all objects accelerate at the same rate due to gravity. And we'll come back and look at some of this later in the class. Galileo is also known for the telescope. He did not invent the telescope, but he was the first to observe the sky and record and publish his observations. So he gets credit for it because he was the first to actually publish his observations. Perhaps other people looked at the sky, but if they did not record their observations, we have no way of knowing this. So let's go ahead and look at what Galileo looked at. What are you going to look at with this new device? Well, you're going to look at some of the brightest objects, the sun, the moon, the bright planet Venus. And what he found was that the sun had spots. It was not perfect. Remember that one of the things that Aristotle said about the heavens is that they were perfect. Well, he found out that the sun was not perfect and that it did rotate, and he could measure that rotation. The moon was also not perfect because it had mountains and craters. So that was another thing here. And let's take a look at his sketches of the moon here. So the moon was not a perfect sphere. It actually was deformed a little bit and had all sorts of different craters that were seen at various times. But one of the key observations that he gave was Venus. When he looked at Venus, he saw that Venus had a complete cycle of phases. Now this meant that Venus must orbit the sun. So here's what he saw. He saw that it could be visible as a large thin crescent, or a smaller thicker crescent, or an even smaller half phase, or a very small full phase. So he saw these various phases of Venus and the size changes. That means that Venus had to be getting closer to Earth at some times and further away at others. But in order to see phases like this, it also means it had to be on the other side of the sun. So what that means, to explain the phases that he saw, again, this is a prediction. You think about the scientific method. We are going to use the scientific method to decide which of these models will work. Well, in order to see this, in order to see the gibbous or the full phase, which would be exactly opposite, you would have to have Venus on the other side of the sun. Now, in Copernicus's model, that was the case. Earth moving around and Venus moving around. And while Venus would always be close to the sun, it would not, it could be on the other side. Under the Ptolemaic or geocentric model, Venus always had to be between Earth and Sun. That was the only way you could explain its motions. So this was a big key for the heliocentric model. It really said that at least one object, Venus, had to be orbiting the sun. So what other objects must orbit the sun? Well, let's look at his other observations here and what else he showed. What other objects he looked at were Jupiter. Jupiter had 4 satellites orbiting it, shown in his sketches here, the circle being Jupiter. And then the stars around it, where the stars around looked to be stars around it, determined to be moons, were actually orbiting. Now, this was also a key discovery. Even though it didn't prove anything about the Earth, it did mean that not everything must orbit Earth. Just as we would have previously thought everything was orbiting Earth. Now we're seeing that things can orbit another object. He also looked at Saturn. Saturn had 2 lobes, so he saw things like this, where he'd see 2 blobs on either side, or this. He didn't quite have enough power to resolve it into the rings. But again, Saturn was very unusual and not perfect. Finally, looking at the Milky Way. Milky Way, which looks like just this patch of dull light on the sky, was actually made up of countless stars. So there was an infinite number, or a much larger number of stars present than might have been previously thought. Now, one of the things that Galileo is best known for was the Inquisition. And he published his observations in 1610. And in 1616, any books supporting the heliocentric theory were considered heretical and were banned. So that would include Galileo's books. Now you see there's a gap here. Galileo was working on other things as well. But in 1632, he had thought at least that the climate had changed enough that he published his great book, Dialogue Concerning the Two Chief World Systems. And the 2 chief world systems were Copernicus's heliocentric model and Ptolemy's geocentric model. And because of this, he was actually found guilty of heresy, because what he was told he could not do was to hold, teach, or defend the heliocentric view. And he was placed under house arrest until his death in 1642. Now, he was eventually vindicated because we found out that Galileo was right. So in 1820, his and Copernicus's books were removed from the index of banned books. But it was not until 1992 that Galileo was formally cleared of charges by the church. So what happened here? Well, like most things that happened this long ago, we're never going to know for sure. But one problem, we can think about some things, is that there was no proof for the heliocentric theory. His observations of Venus were important, but really couldn't prove that the Earth was moving. That proof of parallax would not come until long after his death. There were also a lot of political things going on, including the Reformation that had been occurred not that long before. And the church was losing power. So a struggle to hold on to the power that it had. And there was also probably a lot of internal politics that we will never know about going on internally within the different parts of the Vatican. Also, Galileo was known, his personality was not the sweetest. He did not have the sweetest disposition and could have a rather abrasive personality. And his book did portray the defenders of the geocentric theory. And one of those was considered by some to be represented by the Pope, and looking at them as simple minded. So some of those things just put together really apparently led to all of the issues of Galileo with the Inquisition. Now let's go ahead and finish up with our summary. And what we've looked at is that Copernicus gave us a heliocentric model of the universe with the Earth actually moving. It explains retrograde motion simply, but required parallax, and we did not have any measurements of parallax yet. We also talked about Galileo. He made and published first telescopic observations of many astronomical objects, and he did find a lot of circumstantial evidence to support the heliocentric model, but he could not prove it. And we looked a little bit about how he was tried and convicted by the Inquisition. So that concludes this lecture on the origin of modern astronomy. We'll be back again next time for another topic in astronomy. So until then, have a great day, everyone, and I will see you in class.